Thank you. Right, so this talks about protecting performance. So the last 4 talks I think I have is about how we've looked at measuring performance. Now we're looking, as we're getting closer to go live, to how can we protect the performance we have? In other words, how can we stop people from spamming or breaking our network? So why do we need to protect our network? The network, when we run it, we don't have control over the nodes. We don't have control over the hardware they use. And certainly the network isn't infinitely scalable. The amount of users we hope to get on board and using the system will get bigger and bigger over time, and their resources will be massively larger than the resources we have to handle their requests coming in if they all decide to hit us at the same time. We have different transaction types that will result in different resource usage in the network. So if we send through a new order, that might be quite light. If we send through a cancel all, that cancels 1,000 orders, that's going to generate a lot of work. So we need to be able to differentiate between those and know how to handle them in a fair way inside the network. We have this very fine balance between maximizing the network usage and not being overloaded. So we want to make available as much of the system as we can without it causing problems and overloading so that the performance degrades. So I broke this down into 5 areas where we actively do something to try and prevent performance issues. The first one is sending transactions into the system. How can we control the amount of transactions that enter into the network? So this is people sending in orders, raising proposals, sending in votes, anything like that that goes onto the chain. Then we have the processing of blocks. So once the consensus system has decided what blocks we have, how do we make sure that we can process the blocks in a reasonable time without increasing our block length? Once the blocks have been processed, we then generate events. How can we make sure that the data node is handling those events in a timely manner and we're not getting backlogged and bottlenecked from there? And the last 2 are to do with the data node, and that's for people that subscribe to subscription-based APIs that stay open and give us data, and calling one-off API endpoints that just get one set of data. How can we make sure that we don't overload the data node with people trying to do those? So if I start with the first one, sending transactions into the network. If the user was able to send as many transactions as they wanted into the network, there's a chance they would fill up Tendermint's mempool. And that can lead to multiple issues. It means that new orders might get rejected because the mempool's full. It means that there's a delay from the time a new message gets onto the mempool before it actually gets turned into a block and passed to the system. So ideally, we want the mempool to stay as close to empty as possible so that we get the minimum latency for new orders coming in. And the way the system handles that is to basically make each client pay for a transaction that's being sent in by doing a proof of work step. And if we look at the network parameters, we have 4 network parameters that are defined how that proof of work step is handled. We have a base difficulty, so spam.power.difficulty, which is how much, basically how many zeros in the end of the hash that proof of work has to do before it's accepted. We can specify the hash function. So if in the future we find out that GPUs or a certain piece of hardware makes doing this hashing trivial, then we can swap it to a different hash function. We have an option called increased difficulty. So if a user has used up their amount of transactions in a block, they can keep generating new transactions, but the difficulty will increase for each set that they do from there onwards. And the last one is number of past blocks. When we do a proof of work, we map it to a previous block. We use the hash from a previous block as part of that calculation. This says how many past blocks we can go back into the past to use. This has 2 good things. It allows people to use previous blocks to generate more transactions as a burst. It also gives people a chance to pre-do blocks and then hold on to them for a certain amount of time before sending them to market. And we also limit the number of transactions per block that each user can submit. And that's another network parameter, spam pow number of transactions per block. So this is for one public key, how many transactions per block they can sign at the current difficulty. If we have the increased difficulty option on, then they can sign more per block, but every number of TX per block extras they do will increase the difficulty by 1. And if you think an easy way of getting around this is just to put them into batches, you can to a certain amount, but then we have a batch size to prevent people from just putting 10,000 things into a batch. So we can limit the amount of orders they have in each batch that they send off. So combined, using all these spam options, it limits the amount of transactions a single client can send into the network at once. So the next part is processing blocks. So once we have a block that's agreed by consensus, we pass it down to core. And we need to make sure that we don't send in too much information in the block for the core to handle in a decent amount of time. And we have two network parameters for this. We have a default gas and a max gas per block. So what we do is every time a transaction comes in, we give it a gas cost, and then we add up the amount of gas for all the items that are in that block. And if it's below the certain amount, we allow it through. The max gas per block is what we use to cap that. What this does on the inside is it allows us to treat different markets, different conditions differently. So if we have a market that has a lot of pegged orders and someone tries to add a new pegged order, it will cost them more gas to add that. If they've got a market where there's 20,000 price levels, if they go to add a new price level, it will be harder, will make the gas cost more expensive. On the flip side, if it's a very small market and you've only got, say, 100 orders on the book, it'll be much easier to get transactions through to that market. So it's a way of us adjusting how many transactions can come in depending on market conditions. Once the transaction's been processed, it generates events which are passed out to the data node. The data node can handle a certain amount of events per second. Our way of controlling that is by doing the two previous things we've just talked about. By reducing the amount of transactions that can go in and forcing these gas costs on it to control it, there will be less events generated. So if we find that the data node is struggling, our way of coping with that is to make the previous two things tighter to reduce the amount of input coming in. We also have a buffer between the core and the data node, so that if we do generate bursts of events, we can buffer them and process them slowly, as hopefully quieter times will come just after it. Now, the two ones for the data node, if a client, say at the front end, the console connects to the data node and wants to get a subscription on something like orders or market depth, each one of those will generate work for the data node. So our way of controlling that is to have a limit by the maximum amount of subscriptions per client. This is a setting that's set when we start up the data node, so it's not something we can change at runtime. And it's also very dependent on the hardware that the data node's running on. So this is left up to the admin who's running the node to decide how much hardware, how much bandwidth, how much network bandwidth they've got to set an appropriate maximum subscription count to limit the amount of people that can connect. And last is just calling the API endpoints. So these are one-off data lookups. And this we have a rate limiting system built in. So when this is enabled, we have these two settings, burst and a rate. Every time an API request is made, we take away one from that burst value. So burst value is like the max. And then every 1 second, we increment that bucket or burst value by the rate limit. So this basically allows us to send off 100 orders really quickly, and then we're blocked. And then every second, we get 20 more tokens, so we can do 20 more API requests per second. This is limited by IP address. And again, it's configurable at startup. So depending on your hardware and your network, you can set this to an appropriate value. And this way stops people from spamming requests and taking up the data node. So do we think these settings will work? Maybe. The thing is, we don't really know what the network load is going to be, how many transactions we're going to get, how many markets. So this is our approximation of what we think will keep the network safe, keep it up, stop it from being overloaded, and get it running for now. Many of these settings we can change at runtime because they're network parameters. So if we find we're being too restrictive or we need to tighten up a bit, we can change them with a vote. And the more we see, the better we're going to get. So as we go live, we've got some excellent monitoring. We'll be able to see how things are working, and we can fiddle with these numbers until we get the best usage of our resources. And that's it. Do we have any?